Intermediate Algebra Section 3.3, Solving Application Systems, involving two equations, and we're going to take a look at some motion problems. In other words, distance. In this first example, they're giving us that a car leaves Somerville and travels due east at 56 miles per hour, and at the same time a truck leaves Somerville and travels due west at 48 miles per hour. In how many hours will they be 260 miles apart? There's a lot of information here. They're talking about the car leaving and traveling due east, so sometimes drawing some kind of representation of what's happening helps us to visualize the problem. A car at the same time is leaving Somerville, a truck that is leaving Somerville at the same time it's traveling west, and the question is, how long will it take for them to be 260 miles apart? So their combined distances are equal to 260, and the question is, when will that happen? The other formula or value that we need here is the fact that we're dancing around distance formula, and distance is found by taking rate times time. And this is the basis for creating this table that I have. To help organize the information, I have rate, time, and distance, where we will multiply the rate and give us a resulting distance. There are times when certain problems are actually easier in one variable, and other times it's to our advantage to have the two equations. In this first one, I'm going to work with one variable, and let's get started. It tells us that the car is traveling at 56 miles per hour, so our rate is in miles per hour, which would mean our time needs to be an hour as well, so that the units are in agreement. The truck is leaving at Somerville and traveling at 48 miles per hour. They're leaving at the same time. We don't know what that time is, but their total travel time will be equal to one another, and we're interested in what that total time is that results in their combined distances equaling 260. So I'm going to use t for both of these since they both left at the same time, and at some point in the future their combined distances equal 260. Filling out the rest of the chart, rate times time will give us distance, so we'll have a 56t for the car, 48 times t for the truck. And we're ready to write our equation then. The car's distance, which is 56t, and I guess I'll write that, the car's distance plus the truck's distance, which from our table is 48t, equals the total distance that we're looking for or talking about in this problem, which is equal to 260. Well, simplifying our equation, we have 56t plus 48t is 100. 4t is equal to 260. Solving for t, we'll divide both sides by 104, giving us a value of t is equal to 2.5 hours. Of course, we want to check and verify plugging in 2.5 hours into our equation or the table and make sure that these two distances do end up equaling 260. In this next example, I'm going to use two equations and two unknowns. Here it states Lori starts jogging at 5 miles per hour. 1/2 hour later, Sarah starts jogging on the same route at 7 miles per hour. How long will it take Sarah to catch Lori? So just to represent this, we have Lori, who is starting out jogging, and then a half an hour later, Sarah is starting out, and because she's traveling faster, she eventually will catch up to Lori, so that catching up means that their distances are going to equal one another. The rates that they're talking here are miles per hour, and our time should also then be in agreement, so that our time is in hours. Our distance then would be in miles. Well, Lori is traveling at 5 miles per hour, and it tells us a half an hour later, Sarah starts jogging at 7 miles per hour. We don't know the time Lori has jogged, so we'll let that represent t. And since Sarah is starting a half an hour later, her time to catch up with Sarah is going to be a half an hour less. So we'll say it'll be Lori's time minus a half an hour. And because we want it in hours, we'll leave it as 0.5 rather than perhaps converting it to 30 minutes. Their distances, because they're going to catch up, will be D, our second unknown. From the table and the relationship of rate times time equals distance, we can generate two equations. 5 times t will equal d, which is Lori's information. Sarah's distance then will be 7 times t minus 0.5 will equal d. We have two equations and two unknowns, and in this example, because they're solved for d, we can use substitution. If we take our first equation, 5t equals d, we can replace d with its equivalence in the second equation. So in place of d, since d is also equal to this, we have 5t is equal to 7 times t minus 0.5. And from here, we can solve the equation. We'll use distributive property to simplify on the right. So we'll have a 7 times t and a 7 times negative 0.5, or a negative 3.5. Getting the variables together, let's subtract a 7t from each side. Leaves us with a negative 2t equal to a negative 3.5. And last, to get the variable by itself, divide both sides by negative 2, leaving t is equal to a positive 1.75. Or we could call this 1 3/4 hour. Now, what was our t and what were we looking for? It's asking us how long will it take Sarah to catch up with Lori. We found t, which is Lori's time. We want to know how long it will take Sarah. So we need to know Sarah's time. And Sarah's time is t minus a half. So we'll take our time for Lori's full jog of 1 3/4 and subtract a half from that, which ends up with a 1 1/4 hour for our final solution. And again, it's always a good idea to check your values and also be sure that you're answering the question that the problem is asking. It felt like we should be done here, but it didn't ask us how long did Lori jog. It's asking us how long did ultimately Sarah jog to catch up with Lori.